We live in a world that feels familiar. We understand its rules. You can move forward and backward. You can move left and right. You can also move up and down. These are the three dimensions of space we experience every moment of our lives. They define our reality from the chair you are sitting on to the vast distances between stars. It is called string theory. These are the strings of string theory. They are incredibly small, far smaller than an atom, a proton, or anything we can observe with our most powerful instruments. Think of a guitar string. When you pluck it, it vibrates. Depending on how it vibrates, it produces different musical notes. String theory suggests that the universe works in a similar way. When physicists tried to build a consistent theory based on vibrating strings, they ran into a problem. The equations simply did not work in our familiar world of 3 spatial dimensions plus 1 dimension of time. It produced nonsensical answers, like probabilities that were greater than 100%. The mathematics of string theory only becomes consistent and logical if the universe has more dimensions than we see. Specifically, the most promising versions of the theory require a total of 10 spatial dimensions and 1 dimension of time. That is our familiar 3 dimensions of space, plus 7 more that are completely hidden from us. From a great distance, perhaps from an aeroplane flying high overhead, you would not see the hose's thickness at all. But as you get closer, you see the hose has a second dimension, its circular surface. A small insect, like a ladybug, could crawl along the length of the hose, but it could also walk around its circular body. String theory suggests our universe is like that garden hose. But string theory also says that at every single point in this vast space, there are other dimensions curled up, just like the circular dimension of the hose. They are wrapped up so tightly that they are imperceptible to us. String theory offers a radical and beautiful alternative. It asks us to forget the idea of point-like particles altogether. They are minuscule, one-dimensional filaments of energy. These are the famous strings. They are the fundamental alphabet of the cosmos. Each distinct pattern of vibration corresponds to a different kind of particle. Imagine one particular string vibrating in a simple, gentle pattern. This vibration might manifest itself in our world as a photon, the particle of light. The universe, in this view, is a grand cosmic symphony. These potential shapes for the extra dimensions are known as Calabi-Yau manifolds. They are breathtakingly intricate, with twists, holes, and folds that defy easy visualization. The properties of our universe, the things that make reality what it is, are thought to be written in the very fabric of this hidden, 6-dimensional geometry. Mathematicians estimate that there could be a colossal number of them. Think of it as a cosmic library, filled with an almost infinite number of books. Our universe, with its specific laws, would correspond to just one book in this unimaginably vast library. The primary tool in this hunt is the Large Hadron Collider at CERN, which is the most powerful particle accelerator ever built. By smashing protons together at nearly the speed of light, the LHC recreates for a fleeting moment the incredible energies of the early universe. One of the key signatures physicists are looking for is evidence of supersymmetry. Another dramatic signal would be the detection of missing energy. If a collision at the LHC creates a particle like a graviton that can escape from our 3-dimensional brain into the hidden dimensions, it would vanish from our detectors. We'd see the debris from the collision, but some energy and momentum would appear to have disappeared, a telltale sign of a dimensional leak. The most extreme conditions our universe has ever experienced were during the first moments of the Big Bang. The universe, for a fleeting instant, was truly 10-dimensional. As the universe expanded and cooled, the extra 7 dimensions would have collapsed and curled up into the tiny, compact shapes we believe they have today. This violent process should have left an imprint on the cosmos. This imprint might be detectable today in the form of gravitational waves, but the Big Bang itself should have produced a background of primordial gravitational waves, a faint echo of creation that still permeates all of space. String theory predicts that the process of the extra dimensions collapsing would have created a unique signature in this gravitational wave background. Our journey through the hidden dimensions of string theory has taken us far from the familiar world of our everyday senses. We've explored a cosmos built not on solid points, but on musical vibrations, a reality with more dimensions than we can perceive, whose fundamental laws are written in the language of an invisible, multi-dimensional geometry. Whether string theory ultimately proves to be the correct description of our universe or not, its impact on science and human thought has been immense. It encourages us to look at the familiar world and see the potential for hidden wonder. The unseen dimensions, whether they're real or just a beautiful mathematical dream, remind us that the most incredible discoveries often lie just beyond the edge of what we thought was possible, waiting for a new way of seeing.